Okay, in Chapter 1, we learned the methods of collecting data. In Chapters 2 and 3, we learned how to summarize raw data using tables, graphs, and numbers. So, as far as the statistical process goes, we've discussed the collecting, organizing, and summarizing parts of the process. Before we can begin the analyzing part, we need to introduce probability, which forms the basis of inferential statistics. Think of the probability of an outcome as the likelihood of that outcome happening. So if something has a high likelihood of happening, it's going to have a high probability. If something has a small chance of happening, it's going to have a low probability. So Chapter 5, 5.1, is probability rules. Probability is a measure of the likelihood of a random phenomenon or chance behavior occurring. Probability describes the long-term proportion with which a certain outcome will occur in situations with short-term uncertainty. Probability deals with experiments that yield random short-term results or outcomes, yet reveal long-term predictability. The long-term proportion in which a certain outcome is observed is the probability of that outcome. Okay, again, a lot of words, probably easier to understand with examples. But let's have a few more words first. The law of large numbers tells us as the number of repetitions of a probability experiment increases, the proportion with which a certain outcome is observed gets closer to the probability of the outcome. In other words, probability describes how likely it is that some event will happen. If we look at the proportion of times an event has occurred over a long period of time, we can be more certain of the likelihood of its occurrence. Think about flipping a coin. Okay, you got a heads or a tails. So the probability is 50%, right? 0.5, that you're going to land on heads or tails. Well, if you flip that coin 10 times, it does not mean that you landed on heads 5 times and tails 10 times. Okay? But if you flip it 100 times, you're going to be a little bit closer to landing on heads 50 times and tails 100 times. If you flip it 1,000 times, you're going to be even closer to landing on heads 500 and tails 500. If you flip it 10,000 times, you're going to be even closer and closer and closer. That's the law of large numbers. Okay, in probability, an experiment is any process that can be repeated in which the results are uncertain. So the result of any single trial of the experiment is not known ahead of time. However, the results of the experiment over many trials produce regular patterns that allow accurate predictions. For example, an insurance company cannot know whether a particular 16-year-old driver will have an accident over the course of a year. However, based on historical records, the company can be fairly certain that about 3 out of every 10 16-year-old male drivers will have a traffic accident. Okay, be careful. Probability is a measure of the likelihood of events that have yet to occur. Prior to flipping a coin, we say the probability of observing a head is 1/2. However, once that coin is flipped, the probability is no longer 1/2, since the outcome of that flip has been determined. Okay, the sample space, which we'll say is capital S, of a probability experiment is the collection of all possible outcomes. So let's move from, well, let's just talk about flipping a coin. Your sample space is heads or tails, anything that's possible to get. I was about to say let's move to a die, right? A single 6-sided die. Your sample space would be 1, 2, 3, 4, 5, or 6. Anything that's possible. An event in any collection of outcomes form a probability experiment. An event is any collection of outcomes from a probability experiment. That makes more sense. Okay, so an event is any collection of outcomes from a probability experiment. An event may consist of one outcome or more than one outcome. For example, let's say our event, if we're talking about rolling the die, is rolling an even number. Okay, then that's a 2, a 4, or a 6. We're going to denote simple events with one outcome as E sub I. In general, events are denoted using capital letters again, such as a capital E. Okay. So here's an example. Identifying events and the sample space of a probability experiment. Let me get my pen. Consider the probability experiment of having 2 children. Identify the outcomes. Okay, that's anything that's possible. So one outcome is that they're both boys. One outcome is you have a boy first and then a girl. Or you have a girl first and then a boy. Or they're both girls. Those are the outcomes. The sample space is all the possible outcomes. Basically, the only difference is our notation. We can now call it capital S, and this is our set notation, right? We're going to group these things in brackets, and we can say, oh, so the sample space is every single possible outcome. I don't know why I'm putting commas between these things now. Actually, I don't like that. I'm going to take it off. There. Define the event E, have one boy. So that event can happen by either a boy first or second, but not first and second, right? Okay, makes sense? Okay, here's a couple of rules of probability. The probability of any event E, and here's our notation for that, and it's read the probability of technically event E, I'll just shorten it to probability of E, has to be greater than or equal to 0 and less than or equal to 1. Okay, so your probabilities are always decimal or fractional numbers in between 0 and 1. Think about changing those decimals or fractions to percentages. Okay, so this would be between 0 and 100%. Okay, something you can't have a negative percent chance of something happening, or you can't have 200% chance it's going to happen. 100% means it will happen. 0% means it will not happen. So all probabilities have to be between 0 and 1. And the sum of the probabilities of all outcomes must equal 1. In other words, 100%. So your sample space, when you add the probabilities of each event, it better equal 1 because you have to account for 100% of the possible outcomes. Okay, a probability model lists the possible outcomes of a probability experiment and each outcome's probability. So like this. This is about colors of M&Ms, and it lists their probability. So it's a frequency distribution table, except one of our columns is the probability of each event occurring. Okay, a probability model must satisfy rules 1 and 2. So here's an example. It says, in a bag of peanut M&M milk chocolate candies, the colors of the candies can be brown, yellow, red, blue, orange, or green. Suppose that a candy is randomly selected from a bag. This table shows each color and the probability of drawing that color. Verify this is a probability model. To be a probability model, we got to show that rules 1 and 2 are satisfied. So, rule 1 says all your probabilities have to be between 0 and 1. Check. Rule 2 says that all of your probabilities added together have to equal 1. So plug these in your calculator. Instead of doing that, it's quicker sometimes to just do it by hand. So this is 0.46, 0.61, 0.73, and then I'm going to add this one again, so 0.851. These all added together equal 1. So therefore, this table is a probability model. If an event is impossible, the probability of the event is 0. And if it's certain, the probability is 1. Okay, we already mentioned that. But also, the closer a probability is to 1, the more likely that event's going to occur. The closer a probability is to 0, the less likely it's going to occur. Okay, be careful of this interpretation though. An event with a probability of 0.75 does not mean it has to occur 75 times out of 100, right? It's rather that we expect the number of occurrences to be close to 75 out of 100. The more repetitions of the experiment we do, the closer the proportion gets to 0.75. An unusual event is an event that has a low probability of occurring. Okay, and so typically an event with a probability less than 5%, 0.05, is considered unusual. But again, be careful. That's not a set in stone cutoff point. The researcher and the context of the problem determine the probability that separates unusual from not so unusual. For example, let's say, suppose the probability of being wrongly convicted of a crime punishable by death is 3%. Even though 3% is below our 5% cutoff rate, this probability is still too high. We would not consider that unusual enough. We want this probability to be much closer to 0. But on the other hand, now suppose you're planning a picnic on a day that has a 3% chance of rain. In this context, you consider rain being unusual and you'd go ahead and have the picnic. So the point is, selecting a probability that separates unusual events from not so unusual events is subjective and depends on the situation. Hence, we can call up that quote again, lies, damned lies, and statistics. All right, sorry. Got to go there every now and then. Okay, we're going to begin our discussion of determining probabilities using the idea of relative frequency. Okay, something we've already talked about. Probabilities computed in this manner rely on evidence based on the outcomes of an experiment. Okay, so they're called empirical probabilities or also experimental, right? It's based on an experiment. So the E in empirical might help you remember that that's the experimental ones as opposed to what we're going to have later, classic or theoretical. But empirical means experimental. So the probability of an event is approximately the number of times event E is observed divided by the number of repetitions of the experiment. So when we find probabilities using the empirical approach, the result is approximate because different trials of the experiment lead to different outcomes. Say we want to know what's the probability Michael Jordan is going to make, how many free throws he's going to make out of 10. he shoots 10 free throws. Now with Michael Jordan, it might not be different with trials. He might make all 10 every time. So let's say me. Okay, what's the probability that I'm going to make a free throw? I shoot it 10 times, and we see how many I make. And then I'm going to do another experiment where I shoot it 10 times again, and I probably did not make the same number. Okay. Okay. Building a probability model. So, Pass the Pigs is a Milton Bradley game in which pigs are used as dice. Points are earned based on the way the pig lands. There's 6 possible outcomes when one pig is tossed. A class of 52 students rolled pigs 3,939 times. The number of times each outcome occurred is recorded in the table at the right. Okay, and the next slide continues this question. So here's our table once again. Now here's our questions. Use the results of the experiment to build a probability model for the way the pigs land. Remember, all that means is I have this extra column. It's got my probabilities, right? That's all a probability model is. It's a list of all the possible outcomes and the probabilities. So first of all, it may have told us previously, but I'm not going to back up. I'm just going to add these together to see how many times they threw the dice. There were apparently more than one of them. 12, 94, 1344 plus 1294 plus 767 plus 365 plus 137 plus 32. So this total is 3,939. So to find the probability that it landed on a side with no dot, it's just 1344 divided by 3939. Okay, let's round to 4 decimal places. So this is 0.3412. The probability it landed on a side with a dot is just 1294 out of 3999. So 1294 divided by 3939, 0.3285. 7 divided by 3939, 0.1947. 365 divided by 3939, 0.0927. 137 divided by 3939, 0.0348. And finally 32 divided by 3939. Sorry, had a typo there. Let's do it again. 3939. 0.0081. Now, if I want to double check myself, I can add all these up, and they better be very close to 1. Now, due to rounding, they may not be exactly 1. Again, if I had to use the fractional notation here, they would be exactly 1. So estimate the probability that a thrown pig lands on the side with a dot. Well, there it is. We've already done it. Right? Would it be unusual to throw a leaning jowler? Oh, yeah. In this case, since we're just talking about throwing nothing really important, we would consider this unusual. Yes, because that probability is way less than 0.05. Okay, while the empirical method gives an approximate probability of an event by conducting a probability experiment, like we just saw, and rolling dice over and over. The classical method of computing probabilities does not require that an experiment actually be performed. Rather, it relies on counting techniques. Okay, the classical method of computing probabilities requires equally likely outcomes. That is so important, equally likely outcomes. Think of flipping a coin. It's just as likely to land on heads and tails. Now, if the coin's weighted, you can no longer use this method of computing probabilities. A die, it's just as likely to land on any one of those 6 numbers, equally likely, unless it's weighted, right? Okay, an experiment is said to have equally likely outcomes when each simple event has the same probability of occurring. Okay, so computing probability using the classical method, and it's just like the experimental method, right? It's the number of ways your event can occur divided by the number of possible outcomes. Okay. Let's look at an example. Okay, suppose a fun-sized bag of M&Ms contains 9 brown candies, 6 yellow candies, 7 red candies, 4 orange candies, 2 blue candies, and 2 green candies. Suppose that a candy is randomly selected. What is the probability that it is yellow? Well, how many yellow were there? 6 yellow. Out of how many total candies were there? 9 plus 6 is 15, 22, 26, 28, 30. 6 out of 30, which is 1 out of 5, which is 0.2. So either of these are perfectly acceptable answers. Pay attention to the way your homework wants you to leave your answer, but this needs to be reduced. And by the way, your calculator will reduce your fractions for you. If you don't know how to make your calculator simplify your fractions, okay, let me know. What is the probability that it is blue? Well, I know there's 30 candies. I just need to know how many of them are blue. 2. So that's 1 out of 15. Or 0.0667 rounded. Okay, so comment on the likelihood of the candy being yellow versus blue. Well, it's more likely to be yellow. And as a matter of fact, it looks like it's 3 times more likely, because 2 out of 30 versus 6 out of 30. So we'll say 3 times more likely to get a yellow M&M than a blue one. Okay. There are also subjective probabilities. The subjective probability of an outcome is a probability obtained on the basis of just personal judgment. Okay, for example, an economist predicting there's a 20% chance of recession next year, that would be a subjective probability. Because we can't conduct an experiment n times to obtain a relative frequency. Okay, the economist just uses her knowledge of the current conditions on the economy and makes an educated guess about the likelihood of a recession. It's important to understand that subjective probabilities are often perfectly legitimate and are the only method of assigning likelihood to an outcome sometimes, right? What's the probability that you are going to pass this course? That's a subjective probability that only you can answer based on what you know about yourself, you know, your math history, how dedicated you are, how much time you have to devote to it, you know, all kinds of things. So here's an example. In his fall 1998 article in Chance magazine, Hal Stern investigated the probabilities that a particular horse will win a race. He reports that these probabilities are based on the amount of money bet on each horse. When a probability is given that a particular horse will win a race, is this empirical, classical, or subjective? Now, this is denoted to this guy's probabilities, right? So that makes it subjective because it's based upon people's feelings about which horse will win the race, how much money was bet on each horse, right? It's not based on experiments that where you look back at how many times a particular horse has won the race. Okay. Okay. Let me know if you need anything.